In this video, I'm going to talk about adjusted confidence intervals. I'm going to show you why it's arguably important to include adjusted confidence intervals in your analysis and also how to do it. So the main reason that adjusted confidence intervals should be considered when you're creating a report is that ANOVAs and multiple comparisons procedures tend to be based on a pooled error term. And so here's an example in the ANOVA framework where the entire analysis is based on this mean square error term. So we're dividing between groups or between subjects mean square error by the within groups, and this is a pooled error term, and that yields the F value. And if you look at the Fisher-Hayter Q-test, it is also based on a pooled error term. It doesn't take each individual standard deviation into account associated with each group. It actually uses the entire ANOVA within subjects mean square error. And of course, that's based on the assumption of homogeneity of variance being met. So if these analyses and others are based on a pooled error term, arguably the confidence intervals that we apply or we include in a graph should be based on a pooled error term, because typically we report the result of an ANOVA and some multiple comparisons, and then we show a graph with the confidence intervals, and the confidence intervals tend to be based instead on individual standard deviations which are not pooled. These are not pooled error terms. But the program that you use will typically just use these standard deviations to create the 95% confidence intervals, and SPSS is not an exception that way. If you just use the raw data, you will find that it creates error bars. I've already created one here, so let me just take that out and start from scratch. So bar chart here, put that in there, and we can put the grouping variable on the x-axis and the accuracy variable on the y-axis, and we have display error bars here, and we want 95% confidence intervals. Click apply and OK, and here we go. This is what it looks like initially, and these confidence intervals, these are error bars with 95% confidence intervals. These are not based on a pooled error term. They're just individually based, and arguably that's not really appropriate. So the challenge is to create standard deviations that are based on the pooled error term. And the way to do that is to conduct the ANOVA and get the mean square error based on the raw unadjusted data. So I've got accuracy in the dependent variable and group as my factor variable, and I want to make sure I got my descriptives just to show you what we're dealing with here. And we have the ANOVA mean square error of 234.603. And the way to get a quick way to get the pooled standard deviation is to simply square root this value. So I did that earlier, so 234.603 square rooted gives you a value of 15.317 rounded. That is what should be the standard deviation for each of these four groups, because they're based on a pooled error term. So if they're pooled, it should be equal across all four. And of course, we test the assumption of homogeneity of variance. And if that's satisfied, it assumes that these variances are all from the same population. And it implies that we can calculate a pooled error term. So how can we get SPSS, for example, or any other program, to get data appropriate for creating 95% confidence intervals based on a pooled standard deviation? Well, now that we have the value of what it should be, 15.317 is what it should be, you can see that that's pretty close to what, if we just calculated a simple average of the standard deviations, you'd get something pretty close to this. It's not exactly the same because there's an n-weighted component to it, and the truth is that it's actually based on an n-weighted variance term, not an n-weighted standard deviation. But we can just square root the m square error, and we can get the pooled standard deviation really quickly. So now we need to create it for each data point so that each group can be used to calculate or to create the error bar. So to do that, go into data and aggregate. And the first thing we want is we want a mean for each group separated. So I'll show you what that means. We want the break variable to be grouped, and we want accuracy as a mean. So click mean here, make sure that's selected. And what's going to happen is that SPSS is going to create a variable with the mean for each group. So notice how all these participants have the same mean, 73, 62, and if you keep going, each group actually has its respective mean. So those are the means for each of those groups. So if I go back here, 73, 61.99, 50.8, that's what SPSS is actually creating here. It's created a variable for each respective group that corresponds to the mean. Now the next thing I need is the standard deviation. So I want to transform data, aggregate, and this time here I actually want a different function. I want the standard deviation because I need to create z-scores. And I need to create z-scores for each respective group that is going to be consistent with a standard deviation equal to 15.317. So now that I have the standard deviation for each respective group, so it's 14.9 for group 2 and 13.6 for group 1, I can calculate a z-score. So accuracy adjusted is what I want to create here. And what I can do is I first need the mean, if you recall how to create z-scores. So I want to subtract each variable, accuracy z-score. So I want to create each variable such that it has a z-score. So accuracy minus the mean divided by the standard deviation. And I want to put that into parentheses. And that's going to create the z-scores I need to then ultimately transform into accuracy adjusted scores that have a standard deviation of 15.317 for each group. So now just one more transformation, accuracy adjusted, and now I want to have each group's mean, because I want the same means for each group. I just want adjusted standard deviation so that they're all 15.317. So now I'm going to add the z-score multiplied by the standard deviation, 15.317. 15.317. So that should be right. Accuracy Z, yep. And now I've got this adjusted variable, which is 42.99 for case 1. So that person's score has been adjusted from 46.35 down to 42.99. All the scores have been adjusted in a minor way, but all the means are going to be the same. So let me prove that to you right here. I'm going to conduct an ANOVA on both the accuracy and adjusted accuracy variables, and I want the descriptive statistics. And you can see that each group, this is the original accuracy data. These are different standard deviations for each group. But then for the adjusted data, the standard deviation is equal to the pooled standard deviation derived from the mean square error. The means, however, have remained the same. I've got exactly the same means. And look how the ANOVA, you get exactly the same result. If you base it on the pooled standard deviations derived from the mean square error, you actually get exactly the same F value, which I think is proving that this technique is actually a legitimate one, a valid one. Now, for the final step, you want to actually create your confidence intervals based on the adjusted data, not the original data. So I'm going to put accuracy into there and click OK. And here is the adjusted 95% confidence intervals. Now, the confidence intervals are different in width, even though they're based on equal standard deviations, because the sample sizes are different. So the clinical psychologist with a whopping 209 is going to have a small confidence interval, even though it's based on the same standard deviation of all the groups. It's because sample size is taken into consideration when you calculate 95% confidence intervals. So arguably, these are the more accurate 95% confidence intervals. Now in this case, it didn't make a huge difference. This is adjusted and this is unadjusted. You can see that the FA group, federal agents, the 95% confidence interval is a bit wider. You can see how it comes down lower than this unadjusted group. So it's a little bit bigger. And the PO group is a bit smaller. This is a bit smaller than this here. And those are some of the biggest differences between the two. Now in other cases you'll find bigger differences where perhaps the standard deviations are a little bit more different, and the sample sizes might be all equal. You might see some differences, there. So I don't know if you have to do this, whether reviewers expect you to do it when you're doing a thesis or when you're doing a report, but it's certainly impressive to be able to do it, and it's definitely consistent with the ANOVA and multiple comparison framework.